So last time we were discussing about surface tension, surface energy. We defined the surface tension and surface energy, and also the work of adhesion. So surface energy is basically the amount of energy created when a unit surface is formed, and for liquids we call it surface tension, which is the energy created when a unit length of the liquid surface is formed. So one equation we have seen is this one, which is work of adhesion is given by this equation. So this is also known as Duper equation. And also for cohesive, means if the two materials are same, then we can define the work of adhesion as two times the surface energy. Another thing we saw was Young's equation. So Young's equation is given as gamma SA. So surface energy of the solid in the presence of air as equal to surface energy of the solid and liquid interface plus surface energy of liquid and air interface and theta, whereas theta angle is this one. So this is the contact, the droplet on the solid surface. So here if you see in our case we are interested in this one, gamma SA or gamma S. Sometimes gamma S we write just ignoring A, but we should know that A is always there because these are all interfacial surface energy. That means there has to be two media present. So our interest is often to find out gamma SA, and gamma LA, which is the surface tension of the liquid, is already known because for most of the liquid surface tension is easy to measure and it is known. Theta we can measure by doing an experiment. So we drop a droplet of the liquid on the solid surface we are interested in, and then we can find out theta. And we also need to know gamma SL. Okay, so there is a experimental way of handling this one, and also there is some theoretical method of finding out gamma SL. In both cases you need to have three liquids, so it is also known as three liquid method. Three liquids, we need to have three liquids to find out this gamma SL. And if we are going to use the experimental way, then what we can do is on a solid surface we drop this droplet of the liquid, and then from the tangent we can measure the contact angle. Okay, this one. So if we use two or three liquids, even with two liquids we can find out, because in this equation if you see, this will be known for both liquids. This will be measured experimentally. So these two quantities are known to us for each equation, each time. So there are two unknowns. So to find out two unknowns we need two equations, right? So we can create two equations by selecting two liquids, and these two liquids should be one polar and one non-polar. So for example, often we use water as one, water is polar, and often we use hexadecane or some other liquids which are not polar, non-polar. So if we use two liquid method, we can find out gamma SA because we will create two equations and we can solve the equation and we can find out gamma SA. So that is one way. And in fact most of the experiments, most of the the apparatus, the water contact angle and surface energy apparatus use this method. Okay. So moving on, we talked about surface forces, different types of surface forces, and we also talked about this Hamaker constant. Okay. So assuming that the bodies, the two solid surfaces, are collection of atoms and they are interacting with neighboring atoms in the material, but they are not disturbing each other. So this is a sort of averaging the effect. So using the averaging effect, we can get these equations for the energy potential and for the force, provided we know the Hamaker constant. Okay. So this area is very active in terms of nanoscale friction and wear, which is also known as nanotribology. So we also talked about how nature uses surface forces for its work. So this is the example of Gecko's feet, and the Gecko actually uses this surface forces between its feet, which contains millions of seta, which is called seta. Singular is seta and plural is seti. So it contains millions of seti on the feet, and this seti basically makes the contact with the surface. So one seti is something like this geometrically, and surface is here, so there will be force acting, adhesive force. Okay. So this is how the Gecko will stick to any surface, glass or wall or any surface, and it can walk. Again, if it sticks like this, then how does it remove the feet, right? Because if the force is so much, then it should not be able to walk. But for removing, it can use this fracturing this this bond, and then it can walk. So, but in our engineering application, this concept is being used now, already being used to find out new kinds of adhesives. So adhesives which do not work like the traditional adhesives where you have to do curing of the material. So these adhesives will work on the vulnerable forces, and it will provide a sticking action. So a lot of research is going on in this field. Next, this list provides a table. Here, this table provides you different equations for different geometrical contexts. So for example, two flat surfaces, then we should use this equation for energy potential and this equation for the force. If we have got two spheres, then we can use this one. Okay. And if we have one sphere and one flat, so this is quite typical case. In many of the experiments we use this way. Sphere or micromolecule of radius r. So these are all bigger size, not atomic. These are not atoms, but bigger size particles. We can use these equations. Okay. And parallel cylinder, then we have got this. So these two parallel cylinders, then cylinder on a flat surface and cylinder on cylinder in a crossed geometry. So this is also a very useful geometry because there is a surface force apparatus which is based on this one. So in this case, we can use these equations and we can find out Hamaker constant or surface energy of different solids, interfacial surface forces. So these kind of experiments are done which can be related to adhesion and friction and wear. So these equations have been derived based on the assumption that D is far less than R, where D is the interparticle, the distance. Here, as you can see, the definition is here. So D is far less than R, because if D is larger, then vulnerable forces diminishes. So as we have seen in the graph, the force graph, it's like this. So this force diminishes to zero value, which is called retardation. So within the 10 nanometer range, you will find most highest amount of van der Waals forces. So if the distance is too much apart, then you don't experience the van der Waals forces. And this is the reason that in normal our daily living, we don't experience van der Waals forces, even though they are always acting. If you touch something, the van der Waals forces are acting between our finger, our hand skin and the surface, but we don't experience this. We don't have to, apply a lot of force to pull our hand outside, away. And the reason being that the nature has already designed things to that way. So for example, our hand skin, if you look at hand skin, it is not perfectly smooth. It has got some roughness, and which we call it fingerprints. So these roughnesses actually will ensure that the distance is not within the 10 nanometer. If it is too close, then we will feel as if our hand skin is sticking to the surface. As well as to the surface that we put our hands on, they are not always extremely smooth. So these things work only when the D is 10 nanometer or less than that. And therefore surface roughness play a very big role. The typical value of Hamaker constant A is given as 10 to the power minus 19 joule. But for each kind of solids, we can find out A by this equation. Where C is defined here. So C is coming from this equation, and rho 1 and rho 2 are the number of atoms per unit volume of the two solids. So it is possible to calculate Hamaker constant if we know the C, but typical value is taken as 10 to the power minus 19 joule. So now in the next part I will discuss the analysis which is used to find out gamma SL from the Young's equation. So I mentioned that in Young's equation we have got gamma SL, gamma LA and gamma SA, and this is theta, and this side is the droplet. Okay, so here gamma LA is known, okay, and we want to know gamma SA, but gamma SL is also not known. So how can we use some sort of theoretical way or theoretical and experimental way to find out gamma SL? Fox in 1963 proposed that surface free energy can be considered as the sum of the separate independent cohesive forces that act between materials, such as dispersion, dipolar, induction, H bonding. So we have seen that these are the kind of forces that are acting on the surface. So therefore Lifshitz van der Waals interaction, the surface energy component can be written as this one. So here this is the surface energy component of LW, which is Lifshitz van der Waals. So this basically defines the apolar component. So on the surface you have got different types of forces, okay, but there are some forces which are because of the polar components like electrostatic or ionic or even hydrogen bond. These are polar components, but there are other types of forces which are non-polar components or apolar components. So surface energy is a sum of the two, the polar component and the apolar component. So this one defines the apolar component, gamma LW. We will call it gamma LW. LW stands for Lifshitz van der Waals. So gamma LW is surface free energy component, and gamma L, gamma D, gamma K are the corresponding components. So these are the individual components. As we have seen that van der Waals forces have different components. So these are the forces. So gamma LW is 1. The LW interaction between two apolar materials, again we are talking about apolars, not polar materials, 1 and 2, is given by Good, Girifalco and Fox combining rule. So this rule has been given by them, so we will take that rule as it is. So the interfacial surface energy between two solids, solid 1 and solid 2, the apolar component is given by this one. So surface energy of solid 1, the apolar component, and surface energy of solid 2, again the apolar component, and whole square. So this is the equation which was given by these researchers, and we will take this one. Okay, so equation number 4.10. So we will use this equation later. Now the polar component, which is also known as Lewis acid-base interaction. So this is the polar component. So polar interaction involves interactions between hydrogen donors and hydrogen acceptors, or more generally electron acceptors and electron donors. So as we know that wherever there is a polar interaction, there will be some electrons involved, and there will be some atoms which are electron acceptors, there are some atoms which are electron donors. So when you have acceptor and donor, then you create this kind of polarity, and because of this polarity the surface energy is produced. So this is the definition of polar part, which is abbreviated as AB. So the polar AB and apolar LW free energies of the interfacial interactions are additives for the total free energy. So total surface free energy will be sum of these two. Okay, so this is very important to understand, that surface energy that we have for any kind of solid surfaces is a combination of two components. One is the apolar part, another is the polar part. So in fact, when you conduct an experiment, many times the equipment can let you separate the polar component and the apolar component, and your definition, your explanation of friction will depend upon the polar part and the apolar part. So, but in general, when we deal with surface free energy, we always call it the total one. We take the total, but we should know that it is a combination of the two, the polar and the apolar part. Now we have already seen that for same material, so here I represents as one material, instead of 1 we have used I here. This is given by this equation. Okay, so the work of radiation is 2 times gamma I. Okay, so in magnitude it is 2I. The sign depends upon whether you are talking about creating the surface or bringing them together. So therefore we can write this equation also in the form of surface energy. So total surface energy is equal to surface energy because of the apolar part and surface energy because of the polar part components. Regarding the hydrogen bond or other kinds of apolar parts, as we were talking about molecule, so H2O, so in this case the hydrogen part acts as a it has got positive polarity and this has got negative polarity. So this is like a electron acceptors and this is like a electron donor. So if this molecule has another molecule coming close nearby, H and H and O, then what will happen? This H has got also positive effect and this has got negative effect. So H2O as a single molecule is neutral, but within this molecule it has got positive side and the negative side, so it behaves as if like a dipole that we were talking about. So there will be some bonding here between the two, and this is bonding. This bonding is known as hydrogen bond. Okay. So this is different from the covalent bond or ionic bond, where there is a sharing of electron or there is a transfer of electron. Here, just because of different polarity, it will come together and it will make a bond. So in fact, H2O is a very classic example for hydrogen bond, and even the molecule is very small, but it exists in liquid form because it has got hydrogen bond. Any other kinds of compounds of this type, this nature, do not exist as liquid. For example, H2S, it exists as gas because these molecules are very small and they exist as gas, but only H2O exists as liquid in the nature because of the hydrogen bond. So it's extremely important, and in fact the solid form of H2O, which is ice, also is a result of strong hydrogen bond. So just I thought I will explain this part. So now the total surface energy has got apolar part and the polar part. The polar, cohesive and surface energy of the material I is given as this one. So this is again is given by these equations, and here gamma plus, here I should write I, and gamma minus are the electron acceptor and electron donor parameters of the surface tension. So this is some parameters that we will discuss later. So this is, by definition, this is defined as these two equations. The polar component of the interaction energy between material I and J is then given as this one. Okay. So this is for single material, and here we have got for the interaction between I and J. So I is one material, J is another material. So just like we use terms 1 and 2, it is same, I and J. So this part is the electron acceptor of I interacting with electron donor of J, and this is electron donor of I interacting with electron acceptor of J. So these are some of the definitions that we can just take them. This has been given by some researchers. Next, the Duper. Yeah.
In previous slide, there is a -2 written.
Yeah. So this, we should use this bracket, and this means adhesive interaction. So the minus sign means attractive, the negative sign implies attractive force. So the Duper's equation is already known to us, this one. So AB means for the polar part, and similarly the surface energy will be written as this one. So Duper's equation is valid for both the polar as well as for apolar. If we want to write for apolar, we can write for apolar as well. So this one is written for the polar AB. Now, using the relationship given in the previous slide, means equation 4.16 and 4.15, and we are just replacing Ij with 1, 2, we can write this. So if you look in equation 4.16, this one, and equation number 4.15, you can use those equations, and you can write from here to here. Okay. So a similar relation has also been proposed for apolar component by small. So again, this has been proposed by a researcher for apolar. So this is for polar, but for apolar it is given by this equation. Okay. So these are some of the parameters which you will see later, that for liquid some of the parameters are known. So we can use those parameters and then we can calculate gamma SL that we are interested in. So equation 4.19 and equation 4.20. So this is for the apolar part, this is for the polar part. So now total work of adhesion or surface free energy is given by this one, the apolar part and the polar part. Thus we can combine the apolar and polar contributions to the surface energy. So we can just write the same as surface energy. So surface energy of 1, 2, the interfacial surface energy between 1, 2 is combination of the polar part and the apolar part, and then bringing in equation 4.19 and 4.20. So if you use these two equations, all the parameters of these equations, and you can easily write this one. So this gives the total surface tension or surface energy of the interface between 1 and 2. Now there is another equation which is known as Young-Duper equation. So this is basically combination of Young equation and Duper equation. So for the case of solid liquid air interface, we can write the work of adhesion as this one. So this is the Duper equation, and Young's equation already we know. This is the Young's equation. So these two equations can be combined together and we can write this one. Okay, so here basically you have got gamma SA, which is given by this. So if you replace this one here, and you can find out this one. So minus free energy of SL, which represents solid and liquid, is given by liquid and air, and 1 plus cos theta. So this is a combined equation, and this is known as Young-Duper equation. So again, this is also important equation, we should remember this. So if you just do a simple analysis, and you will find that this equation. Delta gamma SL, delta G SL, which is the surface free energy of the interface solid and liquid, will be given by these two components, the apolar component and the polar component, and this will be defined by this one. So this equation we have just now seen, this one, equation 4.25b. So now Small's equation for apolar interaction is given as, so this is equation number 4.20. So we have seen this equation here, which we can expand and we can write in this way. Okay, square of this minus 2 times this. So Duper's equation for the apolar interaction may be written as this one. So this is apolar. So we bring this one. So we bring the whole thing, this whole thing here, and finally we get this one, delta G SL for the apolar part as this one. So for the polar component, we use the equation for solid and liquid interaction, which is equation number 4.16. So we have already seen the equation number 4.16. This equation, which is given here. So now what we are doing is we are combining equations 4.26, 4.28 and 4.30. So 26, 4.28 and 4.30, and we are writing this one as equal to this one, and here we are replacing these two components for the apolar part and for the polar part. So you will finally obtain this equation, 1 plus cos theta gamma L. So gamma L is the surface tension, here air is always there, and 2 times these, the apolar parts, and these parameters. Okay, so here if you see, all the parameters related to solid are not known. So this one, and this one are not known. These are not known, and all the parameters related to liquid are actually known, because for liquids these parameters are given. You can find out in some tables. People have calculated these parameters, so these are known. So here we have got theta is also known, and this is also known. So we have got three unknowns here, the related to solids. So it says that we can find out these three unknowns if we use three liquids. So we have to use three liquids. We have to conduct experiment three times. Three times we will get different theta, and three liquids means this will be different, this will be different, this will be different, and this will be different. So we will get three equations and three unknowns, so we can solve it and we can find out these parameters related to solid. After this, we use the equation below to find out gamma SL. So gamma SL is given by and this is by using equation 4.22, this equation, where we just replace 1 and 2 as solid and liquid. So finally we have this equation for gamma SL. So we were concerned about finding out gamma SL, which is the interfacial surface energy between solid and the liquid, and which is given by this one. And here we already know that the parameters which are related to the liquids are already known, and the parameters which are related to solid we have already calculated here using the three liquid method. So these are also known. Sorry, this solid and solid. So all the parameters are known here by using three liquid methods. So that means we can find out, we can calculate gamma SL. So this gives you a understanding about how we can find out gamma SL. And once we get the gamma SL, we already have gamma L, and we measure theta, and we can find out gamma S. So for using any liquid like water or hexadecane, we can use this equation. So this analysis gives us method to find out gamma SL. So there are two ways you can find out gamma SL using three liquid method, or you can directly use this complete equation and find out gamma S again using two liquid method or three liquid method. So here, next slide, we have got some data from books for different liquids. These liquids are generally used, and gamma L, LW, all these parameters we will need. So later I will show you using a tutorial example how we can use these values and actually calculate gamma SL. So these are apolar materials like decane, tetradecane, toluene, and hexadecane 2. Polar are water, glycerol, ethylene, glycol. Okay. So today this is what I wanted to explain to you, this method of finding out gamma SL, again using three liquid method, and then calculating gamma S, which is the surface free energy of a solid. So here A is there, air is there, here also air is there. Okay, using Young's equation. So any question you have?
Sir, these are the very long relationships.
Yeah.
So, sir, should I remember this for exams point of view?
No, you don't have to remember them. I have gone through to make you aware how these equations, how the surface free energy is calculated, how it works, the whole analysis behind it, and the meaning behind it. Okay, you don't have to remember these equations. Whenever equations will be necessary. Either it will be simple Young's equation or Duper equation, or the equations will be given. So that should not be a problem to you. But it is important that we understand, because this is a very basic thing, surface free energy, because this controls friction and wear. And often when we talk about macroscopic phenomenon, we forget about this one. So all the surfaces we are designing for tribological applications, they have to consider the surface energy. And in fact, we do consider. So for example, when you talk about Teflon, Teflon coating, so Teflon, by applying Teflon, we are actually reducing the surface energy. The Teflon has got very low surface energy compared to some other materials like ceramic. So if we are using surface like Teflon coating and ceramic coating, Teflon coating will provide you low friction because of low surface energy and low adhesion, but ceramic coatings will not provide you low friction, even though it is hard. So because it is hard, so it is wear resistant, but in terms of friction, it is not giving you low coefficient of friction. So it is the physics behind the friction adhesion that is acting on the solid surfaces. So this is very important.